Well, welcome back, guys, and I'm really sorry you can't be with me because schools are closed at the moment, but I do hope, as ever, you and your family are keeping well. So what we're going to look at today is a new topic. We're going to look at the topic of waves. What waves are, how we can describe them, and what they do. So the first thing we're going to look at is what the cause of waves are. And waves are caused by any object or medium or material that's vibrating up and down or side to side or even rotating. There's actually one exception to that rule. You can also have waves where there is no material moving, and that's the case for electromagnetic waves. So we're going to kick off by saying the cause of waves is a vibration or oscillation. And we're going to use those two words interchangeably. So sometimes I say the object's vibrating, sometimes I say the object is oscillating. Now, to start off with, we need to look at one particular type of wave, and that's what we're going to call a progressive wave. Okay, so a progressive wave, I think, is the one you're most familiar with. It's a wave that's equivalent to shaking a rope or shaking a slinky or shaking out your duvet in the morning. It's a wave that transfers energy from one place to another. So it's a term you need to know. So the progressive wave, transfers energy. That's its job, really. Now, the really important thing about this is that the progressive wave, the wave that's traveling through space, transfers energy from one place to another, but it doesn't transfer matter. Okay. In other words, let's just talk about waves that have a material to travel in, a medium. That when that medium vibrates, the medium itself doesn't travel from A to B. It vibrates around a fixed point, and it's the energy that moves from A to B. Students are very confused by this. I think they think of water waves going up and down on a beach. But if you think about it, out at sea, if progressive waves carried energy and the medium, every time there was a wave, there'd be a big hole in the sea when the water had travelled away from that point to another point, instead of just bobbing up and down. Okay? So it's important you understand that progressive waves do not transfer mass, so not matter. Now, I've just said to you that they might use a material to carry that energy, so progressive waves transfer energy through matter. To give you one example, for example, sound. When I talk, the sound I'm making at the moment causes a vibration of the air particles, but the air doesn't go chasing off to the camera or chasing off to the microphone. If it did, I'd run out of air here and I wouldn't be able to breathe. It just causes a vibration of that medium or material. Now, I did say to you there's one exception, of course, which is the vacuum. And it caused physicists a lot of confusion for many, many years. What carries the wave? So they went hunting for what carried electromagnetic waves, and they didn't find a medium. They invented one, but they didn't find a medium. So electromagnetic waves can kind of travel on their own. Individual photons carry the energy. So an example of a wave that would go through a vacuum is something like radio. And if you remember, that's an electromagnetic wave. So let's look a bit further at how waves are produced, and I'm going to look at waves in two mediums, either air or water. So air or water. So we know that those materials are made of particles. And we said in the case of a wave travelling through them, the wave transfers energy. So we get energy transfer from A to B. Yep, across the sea, or in the case of me teaching in a classroom, across the room. Now, we know that that's caused by a vibration, so we know that the particles vibrate. But the crucial thing is, they're not kind of vibrating and travelling from A to B. They're vibrating around a fixed point. So, to use the correct physics term, the particles vibrate from or around an equilibrium point. So, what you're imagining there, of course, is that if it's a sound wave and I'm sending sound that way, there's some air particles here, some nitrogen or oxygen, and the sound's going that way, but the particles were sort of, you could imagine them as stationary. Of course, they've got random kinetic energy, but they basically are where they are, and when I produce a sound wave, they vibrate around that fixed point. And in the case of a water wave, you jump into the swimming pool and the water molecules go down and then up and then down and then up from that fixed point before there was a wave, and the wave energy travels out at 90 degrees. Now, what causes them to kind of oscillate? Well, I think it's sort of obvious, but the important thing that you must understand is that if you displace a water molecule or an air particle from where it was, there are intermolecular forces, the same as when you bang a piece of metal and the sound wave travels down it. And it's a little bit like springs between the objects. In other words, if you displace one particle, there's a restoring force wanting to bring it back. You've all seen waves on slinkies, and you pull the spring one way, and then it kind of wants to get pulled back, especially when you stretch it and then let go. Okay, so we've got the energy transfer from A to B in a progressive wave. We've got the particles vibrate from an equilibrium point or position, and you need to know there are restoring forces. And these restoring forces are what brings the particles back to where they were to probably oscillate again to keep the wave motion going. So finally, for this little bit, let's look at the two types of oscillation that we can set up in a medium, or in the case of electromagnetic waves, in a vacuum. And you'll be familiar with these. They're the terms transverse and longitudinal. And you must understand them really, really well. So let's look at transverse vibrations firstly. Okay, they're the ones I always think of as water waves, where you bounce up and down and the wave goes out at 90 degrees. You drop a stone into a pond and the ripples go out in circles at 90 degrees. So the first one that you need to know is the transverse wave. And in the case of a transverse wave, the oscillation or vibration is at 90 degrees to the wave energy transfer. So the vibration is perpendicular to the wave energy transfer. So that's the first one you should know. And the second one is typical of some earthquakes and particularly sound. And you imagine loudspeakers moving in and out like that. And what they're doing is compressing and then thinning out the air, compressing and rarefying the air. And the wave travels in a parallel direction to the movement of the thing that's oscillating. So the other way of making waves that you must know is longitudinal. So if you're asked to describe how a longitudinal wave is made, that's where, I'll change my word, I'll go for oscillation. That's where the oscillation is parallel to the direction of energy transfer. So, you've now got a good understanding of what a progressive wave is and the two ways that the wave can travel from A to B. So I'll take a photograph of that screen now and leave it on for a few moments so you can see what we've just done. So now let's have a little bit of a closer look at how the particles move in transverse and longitudinal waves. So we'll look at the transverse wave firstly. And these things will begin to stretch my drawing skills. So here we go. So imagine shaking out a duvet or shaking a rope. Okay, so you're going to vibrate that way. Okay, could be side to side, it could be up and down, doesn't really matter too much. But in this case, it looks like a vibration that's up and down, and the wave will form like that in the medium. And as a teacher, I'm quite keen to draw this bit as flat, trying to make the point that you've been shaking up and down here for a while, the wave's been travelling this way, but hasn't reached there yet. So those particles are in their equilibrium position. Now, let's have a look at some of the things we can label on here. So firstly, we could say that the energy is going that way. Very noticeable if you do this with another student and you shake a slinky spring here and they hold on to it, and they're always surprised that their hand moves once the wave reaches it. Okay, we've got some other bits that we can label. We've got a peak here. Okay, or you could call that, if you want, the crest of a wave, the peak or a crest. And here, the lowest part of the wave, we'll call that a trough. Okay, it's important you understand about the peaks or crests of waves and the troughs, because we're going to look at what happens when we add two or more waves at a later stage. Okay, finally, let's pick a point on this wave. Let's pick a little point here. Okay, point P. Now that little point on the wave, just make it a little bit clearer if I can. There we go. That point on the wave is currently at the midpoint, so it's at its equilibrium just for a moment. But can you see in a minute this crest is going to travel that way, so it's going to be lifted up and then drop down and lifted up and drop down. So indeed, it's a transverse wave because the vibration or oscillation of each particle and the thing causing the wave is indeed at 90 degrees to the direction that the wave energy travels. So now let's look at longitudinal waves. So the longitudinal wave. Now again, this will test my drawing skills, but I'm going to give it a go. Now there's lots of different ways to draw this one, but I'm going to draw it as a longitudinal wave on something like a slinky spring. So we're going to vibrate parallel to the way the wave moves. So we're going to shake up and down like that, and the slinky spring is going to be long here. Okay. So what happens is you crush up the slinky spring. Then previously you move backwards and you stretch it out. Then prior to that, you'd moved your hands forwards and crushed it up. And prior to that, you'd stretched it out. And then what I'm trying to draw and not doing very well is this bit of the slinky spring. Nothing's really happened there yet. Okay, so we've got a crushed up bit, an expanded bit, a crushed up bit, an expanded bit, and then here we've just got the normal slinky spring coils side by side. So we can see the energy going parallel to the direction the wave travels, to the direction of the oscillator, sorry. Okay, so the energy, I'll say that again, the energy going parallel to the direction that the object that vibrates is going. Okay, and there's two important places that we can label. We've got this area here where we've got a compression, and this area here where the term might be new to you. This area is where the, I'll try and explain this, where the spring is rarer, spread out. It is rarefied, so this is a rare faction. Faction, that's an eighth. Okay, a rarefaction. Word that a lot of students forget, and I seem to have almost forgotten it there. Okay. Finally, what we'll do is pick a point on the slinky spring. Let's pick that one there. Okay. And point P. Okay. And what you've got to imagine, of course, is when you vibrate the slinky spring, the slinky doesn't move across the room. Okay. This point and all the others vibrate parallel to that oscillation around a fixed point around their equilibrium. So I hope you've got a good understanding now of longitudinal and transverse waves and how they work. What I'd like you to do now is pause this video, and in the link above, please watch my YouTube video on slinky waves, and you'll see these waves in action, how they're made and how they travel. And then when you've watched that, come back to this lesson and we'll continue our understanding of waves. Right, so what we're going to look at now is some wave terminology. In other words, the technical terms that you need to describe waves. And some of these you'll know already. But for A-level, you've got to know them inside out. And as I said earlier, this is going to test my drawing skills even further. So I'm going to draw a wave, and then I'm going to label some of the bits of the wave that you need to know well. So we have to use this kind of axis, because we know that the oscillation will be around a fixed point and it'll go higher than that and lower than that. So here is our axis, okay, and I need to label the axes for what we're looking at, but first I'll draw the wave. So here we go. I'll do it in blue, I think, and make it a bit clearer. There's one oscillation. And there's the next one. And I won't draw a horizontal line there to show that the wave hasn't reached that point yet. Okay. Now, what exactly am I drawing here? It's really important you understand this, even if you think you know already. I haven't labelled the axis, but what I'm drawing here is a diver's eye view of a water wave in the sea. In other words, you've popped your head up out of the water and you see the wave ripple past you. You're looking at all of the water, okay? Or it's someone shaking a spring, slinky spring, and you're looking at all of the slinky spring, okay? So it's clear then that this axis is distance in meters along the sea or along the slinky spring. And this up and down here represents how much the spring has moved from one side to the other, or the water has lifted above its equilibrium point or fallen below it. I'm going to have to move over here to do this bit. This is displacement. Okay. Now, We need to know what units we measure displacement in and what letter we use for displacement. Well, d is distance, and it's not a vector quantity. Displacement is a vector quantity. It can go positive or negative, and we need to know in which direction. So for displacement, we use the letter little s. Okay, and it's going to be measured in nothing else but meters. Okay, be a bit careful. You can do it in centimetres, but it's good to stay in the units that we're familiar with. Now, why this letter S, which is so confusing with other things in physics? I like to think about it as separation. Okay, so if we look at a point on this wave, a particular point, maybe here, point P. Okay, we can talk about that as having a displacement of maybe minus 0.3 of a metre. Okay, because it's separated from its equilibrium point, in this case, downwards. Now, there's a name for this type of drawing, looking at the whole wave. Okay, what we're seeing here is all the particles. In the wave. Okay, and therefore, it's kind of a picture of everything that you see when you see a wave. So, it's called the wave profile. I think you can see why it's called that. It's kind of the picture of the wave. Now, I also need to label on some measurements that we can make. And the first thing I'll do, I don't know if I've got a big fat pen here. Maybe this big fat black one might work. Okay, watch this. All the way up. All the way down and back to where I started. Okay, I'm sure you're familiar with this, but there are 1, 2, 3, 4. No, there aren't 4 waves here. There are 2 waves here, all the way up, all the way down and back to where you started. Think of a kid on a swing, all the way up, all the way back and back to where you started. Okay, I always think about this, and later on next year we'll look at this in terms of rotation. In other words, an object that's rotating, is all the way up and then all the way down and back to where you started. We'll talk about which way we actually rotate later on, but you can see that that would be 0 displacement, okay? And then we're going higher and higher and higher, lower and lower and lower, and back again. Now here I was looking at just the tip of the pen. Here I'm looking at the whole wave, but I'm making the point that that is one oscillation, one vibration. Or can you see now why it's called one cycle? Yeah, because we normally describe these terms on waves in terms of mass that goes round in circles. Right, the things you should know already about this wave. You should know what is meant by the wavelength. Now, this is really interesting, okay? The wavelength is the length from, in a straight line, from the start of one wave to the end of that wave. So you get a ruler and you measure that distance. But you've probably never been taught that before, okay? But because these waves are a constant frequency, that if you take that distance and just slide along a little bit, you'll notice I'm level with the 2 peaks. So it's actually much easier to draw your wavelength as this distance. And I point out to GCSE students, when they draw this, don't just kind of draw it. Take some real effort to make sure you've got the distance right. Okay, and that is the wavelength of our wave. It's going to be measured in meters, nothing else. Not centimetres or kilometres if we're going to do calculations. And we're going to give it the Greek capital L, lambda. Okay, so we're going to abbreviate the word wavelength to lambda, and it's lambda in metres. Now, we've got one other measurement that we can make on this wave. Okay, the surfer's measurement, I call it. Calm water. Okay, how high is the wave gone compared to a calm day? Okay, there's a common trick question at GCSE, which is the distance from the trough to the peak. Now, I granted that a surfer would go all the way up and all the way down if they fell off the crest of the wave, okay? But the amplitude of a wave is the maximum positive displacement. In other words, you pick your little particle P, you make sure that it's currently on the zero displacement, and you ask yourself, how high has it been lifted? So this measurement here, that one, is, I'll just have to come down here, is the amplitude. We usually give it the capital A as a letter. We don't do many calculations with it at lower sector level, okay? And it's measured in meters. And just to make the point, the amplitude is little s sub max. Okay. Tricky thing to write that, okay? The amplitude is where the displacement is maximum and positive. But now I'm going to do something slightly different. What I'm going to do here is I'm going to draw just how does that particle P move as time ticks away. Okay, so whilst I'm drawing it, think that what I'm representing here is not every single particle on the wave, the whole of the wave. I'm only representing what one little particle would be doing. So here's my axis. And you'll see in a minute I'm going to have to put different labels on the axis. So there we go. Okay. Now, how does the little particle P bob up and down? How does it displace? Well, okay, I'll come over here for a second. This is going to be S, the displacement. And that will be in meters still. Okay, and the little particle will bob up and down. So I am not drawing this diagram, okay? You'll see in a minute that it'll look identical to that diagram, but it's completely different. Okay, in some ways I should draw it in a different way, but I'll do this anyway. So all the way up, it goes all the way down, it goes all the way up, goes all the way down, and back to where it started. Oh, almost got that right. Okay, and what is this axis then? Well, if this represents just one particle bobbing up and down, what it is a displacement time graph. So this axis is time measured in seconds. Okay, now if you haven't clearly got that in your head and wondering, okay, what's actually happening here? At time t equals 0, the particle is where it was. Okay, it's at its equilibrium position. And then as time ticks away, should we go to here? 0.5 seconds. Okay, you can see between the start of your stopwatch and half a second, that particle has moved all the way up, all the way down, and back to where it started. In other words, we're looking very closely at just one position on the wave. Now, clearly, because we start the stopwatch here, it's not that particle, it's probably a particle just here. That, hang on, sorry, let's get it right. A particle that's going to rise up first, not going to a trough first. Okay, so I suppose you could imagine it as a particle on the wave that's just about to lift up. Okay, so we've got this diagram here. We know that this will be 1 second. Okay, and therefore you can have a close look at this and see, oh yes, 2 waves are here, not 4. Okay, so it takes 1 second to make 2 waves. And I'm going to write up in here in green, just to remind ourselves, we're looking here at the vibration of 1 particle only. Okay. Really important thing at A level and in physics, that we look at maybe 1 ring on the slinky spring and we see, how does that move? Okay, and some of you might think, well, how does this graph represent a slinky spring in a longitudinal vibration? Well, to start off with, that coil was not displaced, and then it was pushed, a positive displacement, and then pulled back, a negative displacement, and then back to where it started in half a second. Okay? You'll notice one thing, though, that's really important, that this is still displacement, so we can still draw on here this distance and label it the amplitude. So whatever if these two represent the same material moving in the same wave, then the value of the amplitude here will be the same value as the amplitude of that one there. So, two really important diagrams of waves there. And what we can do now is drill down a bit further and do a few more terms that we can describe waves with. But before we do you notice that this wave is travelling along through space? And so I suppose we could put on this diagram that in that direction we're looking at the wave velocity. And that's going to be measured in, I'll put it in brackets to make it a bit clearer, meters per second. Or obviously at A level, we really want to say meters seconds to the -1. We want to get away from this kind of notation. Okay, now, careful. Okay, this one, yeah, that way is not velocity. It's not travelling that way. That's a picture of the wave, that's the wave profile. This is a mathematical model of how one particle moves. So we can't put velocity that way. I want to be a little bit careful now, not go too far ahead of myself. But do you remember distance time graphs at GCSE? Do you remember the gradient of a displacement distance time graph did show you the velocity? So velocity is hiding in there, and acceleration of the particle is hiding in there. But I think we'll leave that for another time. But what we can do is we can look at the terminology of the time period of this wave. So I'm going to put time in brackets, because normally we just talk about the period. There's a good reason why I like to call it the time period of a wave. Okay, the time period of a wave, T, capital T, is the time taken for one complete oscillation. Okay, so T here, the time period. Notice it's capital T, so it's not any time on the wave. It is the time taken for the wave to do one complete oscillation, one cycle. For the case above, the time period is 0.5 seconds. Okay, so that lets us realize what the frequency is. Yeah, the frequency of the wave, how rapidly it's oscillating, or how many times it's oscillating per second. And you remember that the frequency from GCSE has a little f as its symbol. Okay, and you'll notice here we get rather interesting units. 2 waves, okay, 1, 2, remember not 4, 2 waves per second. Now I'm not going to write /seconds there, I'm going to do it properly, per second. Okay, so the frequency of that wave is 2 per second. But of course I hope you remember that that was named after Heinrich Hertz, so the frequency of this wave is 2 Hertz. Now, finally on this, you'll notice, if you don't remember, the connection, it's a really important one, between frequency and time period. Okay? If you take the reciprocal of 2, you get a half. If you take the reciprocal of a half, you get 2. In other words, these two relate mathematically. They're the reciprocal of each other. Okay? So, the time period of any wave is equal to 1 over the frequency, and the frequency of any wave is equal to 1 over the time period. Okay, so that's something you really must just know. Okay, it must be just come from your brain very, very quickly. And the main thing I need to point out here is, we really should do the time period in seconds. So this must be per second. So it must be in hertz. And if we're going to do that, we must do that in hertz, not kilohertz. So this must end up, this time period will be in seconds. Be really careful with your units, because obviously we're going to get things like kilohertz and megahertz that could confuse us. So I hope you enjoyed that lesson on waves. That's our first lesson, an introduction to this topic in the A-level specification. I'm going to be making another video now that will take us to the next bit of the topic. So we're going to look at how we can actually measure wave periods or calculate them from looking at oscilloscope pictures. And we're going to look at the meaning of phase in waves. Anyway, do go back and look over this and make sure you've got some of your own notes and that you understand it really well. And when you're ready, let's move on to the next video on waves. I look forward to seeing you then.